Welcome to my presentation about Protograph-based LDPC codes with local irregularity. My name is Vincent Wüst and I collaborated for this work together with Adam Chill and Lauren Schmalen. This work has been presented at ISIT 2025. So when considering the LDPC code design, there's different design frameworks that you can consider. There's very generic types of LDPC codes like the multi-edge type LDPC code, which can model almost every other type of LDPC code. And on the other hand, there's also simpler structures like the Protograph-based LDPC code, which has a simpler design, and it also has the advantage that it has a lower encoding and decoding complexity. Such a Protograph-based code is, for example, the AR4JA that we simulate here on the right. So here you see the bit error rate and frame error rates for this type of code on the additive white Gaussian noise channel, where you see the SNR on the x-axis and the bit error rate and frame error rate. On the vertical line you see the capacity shown as a black vertical line, so below that you cannot perform. And you have the decoding threshold of this type of code, which is characteristic for this code. It's the SNR threshold, and at this decoding threshold the performance starts to be better and the bit error rate starts to drop at this SNR. So this is a type of simulation that you can make use of to compare different types of codes, and we will make use of it when introducing our own types of codes later on. So we introduced a Protograph-based code with local irregularity, or short PLI, and it's a generalization of protographs because it introduces irregularities, and it's still more restrictive than multi-edge type LDPC codes. And with that we build PLIs on top of protographs, and we improve the performance of the code while hopefully maintaining a simpler design than multi-edge type codes. And in the best case, we would achieve to move the decoding threshold from the right to the left closer to the capacity, with this introducing those irregularities. To discuss the PLI, we first need to understand the conventional protographs, so I have a short recap on that first. So basically what you need to consider is a protograph as shown on the left. It's a bipartite graph with variable nodes on the left and check nodes on the right, connected with edges that can be also parallel. And the same information can be represented by the protomatrix, where you have each row represents a check node and the different columns represent different variable nodes. It contains the same information. One particular entry, for example the first entry, which is between the first row and the first column, so between the first variable node and between the first check node, you see that there should be two edges. Which you can see both here in this entry, but also on the graph above. Now, further properties that you usually consider when talking about protographs are the lifting factor, that you need to construct the parity check matrix, the PCM, from the protograph, as well as the design rate, which also depends on variable nodes and check nodes, and also variable node and check node degrees, which are the number of edges that are ingoing to a node. So for example, if you look at the check node 2, it has 3 incoming edges, also counting parallel edges, so it has a total degree of 3. Now we will in this work also be interested in local degrees, so basically a particular number of edges coming from another node to a certain node. So the local check node degree 2, 3 would represent the number of edges going from variable node 3 to check node 2. Now, with this information, how do you go from a protograph to parity check matrix? So as shown before, we have this setting of a protomatrix where each block Bij contains a non-negative integer, and on the right we have the PCM, which is constructed in the following way. So each block Hij is the sum of Bij many non-overlapping permutation matrices of size S times S. So that's where the lifting factor comes in. And each block represents a regular LDPC code. So looking at the first block in particular, we see that value 2 here And we see on the right in the parity check matrix that this corresponds to two non-zero entries for each column and each row. So yeah, this is how you lift the protograph. And in the local, in the PLI setting, so the irregularities, how do they show up? So basically you start again with the proto matrix. And now additionally we also have this local variable node degree distribution for a particular block Bij. And when lifting, now each block Bij represents an irregular LDPC code instead of just a regular one, which can be shown in this first block again. So on the left we have the value 2, and on the right now we see that the different columns have different number of non-zero entries. However, the number of non-zero entries for the row is still fixed, so it's still equal to 2 for each row, and that's where the non-zero, this value 2 comes in, and the degree distribution describes the different columns. Let's look at this example in more detail. So we now consider the local variable node degree distribution with a particular example given on the left, and on the right we see the single block Hij with a bigger lifting factor this time. So basically we have 3 out of 7 columns that have exactly 1 non-zero entry. We have 2 out of 7 columns with exactly 2 non-zero entries, 1 out of 7 with 3 non-zero entries, and 1 out of 7 with 4 non-zero entries. So you see how this single block Hij perfectly replicates this local variable node degree distribution given on the left. Now the local check node degree is still fixed, so it's still regular, so equal to 2 in this example. And this is a design choice, so we fixed this to not have the complexity to grow too much. But you could also define this just the other way around, have a check node degree distribution and the local variable node degree still being regular. You could also do it that way, but we wanted to do it this way. Now this design choice, it also leads to a certain condition, basically saying that the average local variable node degree must be equal to the local check node degree. And with this we can also define the local edge perspective degree distribution, basically defining the fraction of edges connected to variable nodes of a certain degree. And this in the setting, given the necessary condition on the left, leads us to this definition of the local edge perspective degree distribution. So with all those tools at hand, we now know how to describe the PLI, but now we also need a cost function for PLI to optimize those irregularities that we want to introduce. And for this we make use of the iterative decoding threshold, so meaning the various critical channel specification for which the probability of decoding error becomes arbitrarily small asymptotically. And in the case of a Gaussian channel, this means the SNR threshold that we have seen in the introductory slide already. Good, so to calculate this SNR threshold, there's a simple approximation which is called the PEXIT short, or Protograph Extrinsic Information Transfer. And this has a nice advantage that you can calculate it or approximate it using only the channel quality, the channel specification, and the protograph itself. So given that, you run the algorithm and you have an approximation of the SNR threshold. And it basically looks the following way. You have 3 update equations. First, the update of the extrinsic variable node information, going from variable node to check nodes. And it's basically given by the expression here below. We don't really care about how the function f looks like, because this is given by a literature on the PEXIT. For this work in particular, it doesn't really matter too much, as we only need to, the structure of this function doesn't have any implications on our contribution. Now the other two update equations are the update equation from extrinsic information from check nodes to variable nodes, given here. And lastly, the update equation for the a posteriori information. And you see in those three examples, so the functions, they depend on the information coming from the channel, the information coming from the other check nodes or variable nodes, and Bj, which represents the edge configuration of the graph that you're considering, this protograph that you're considering. And with those three updated equations, by running them iteratively, you can see if this converges. So in the best case, this E a posteriori would converge towards 1, and that's how you would know that for this channel specification, your probability of error should be very, very small. Yes, so this is the PEXIT algorithm, and now we investigate how we need to adapt it for the PLI setting to calculate the decoding threshold for our PLI codes. So for this, we need to consider all the update equations individually. So let's look at the first one here. So this is the update equations for the extrinsic information of variable nodes to check nodes. We need the incoming informations from the check nodes as well as the configuration of edges. And in this PEXIT case, all the columns of a certain type of variable nodes, they all have the same amount of non-zero entries, so they should behave the same, and that's why we can define the update equation just like this in the PEXIT case. Now in the PLI case, it's a little bit different because now the columns within one type of variable nodes, they have a different amount of degree non-zero entries. And this we need to take into account. So the edge configuration is not constant anymore. Bj varies now within type J. And this we can take into account by making use of the same function as in the PEXIT case, now in the PLI case, but we need to weight average over different edge configurations basically. That's why we need the second factor and why we need to sum over the different configurations here. And we need to weight it in the following way. So for the most variables, you just take the local variable node degree distribution, but for the edge connection from variable node j to I, we need the edge perspective degree distribution because here we consider a single edge. For the other edges, we take all the information from all parallel edges. Here we consider a single edge, and that's why we need the edge perspective degree distribution. Now for the check nodes update equation, there is no change as we defined it to be regular as in the PEXIT case. But in the case of the a posteriori information, there needs to be a change as well that is quite similar. So basically, again, in the PEXIT case, the Bj is constant. So that's why we have this simple formula that just depends on this one configuration. And in the PLI setting, again, we have this distribution now on the non-zero entries. And that means we need, again, to average over the different configurations of this Bj vector. And in this case, we consider always all edges that are incoming. So that's why we have to weight by the local variable node degree distribution and no edge perspective degree distribution. Now we have the tools to describe a PLI code, and as also a cost function adapted to the PLI setting, the iterative decoding threshold, for which we can now optimize the irregularities that we introduce. So basically, starting from this conventional protograph that we have seen in the introductory slide, so this rate 1/2 AR4JA, we make use of it and introduce irregularities in a way that we optimize the decoding threshold. So we have two approaches. One is the single block optimization, where we just introduce irregularities in one block, the one highlighted in the proto matrix right now. And the second approach, where we introduce multiple irregularities in multiple blocks, highlighted right now, so in 3 blocks. And this, of course, should result in a better decoding threshold because we have more degrees of freedom, so we optimize more the degree distributions and introduce more irregularities. And we did this optimization with the genetic algorithm. And now to the simulation results. So we simulated with a block length of 400,000, which is quite large. We used random permutation lifting, and we removed all 4 cycles in the parity check matrix. And we did this for all codes. And first we show again the simulation results for the rate 1/2 AR4JA code in this additive white Gaussian noise channel setting. This curve you have seen before. And now we achieved 0.3 dB improvement in the decoding threshold when introducing a single irregularity. And also similarly, we don't really observe an error floor and have the same decaying behavior. And now going to the multi-block optimization, where we introduce 3 irregularities, we even achieve 0.4 dB improvement in the decoding threshold. This is good, but in this case we introduce an error floor as visible here, but also visible for the frame error rate shown in the dashed line that is now behaving not very nicely. This is due to the fact that by introducing so many irregularities, the issue is that you now also have more variable nodes of degree 2, and by that your code suffers from an error floor. So to summarize, we developed a generalization of Protograph-based codes. We introduced a new cost function adapted to this PLI setting that allows us to approximate the decoding threshold. And we achieved improvements with this cost function and the PLI codes, improvements of 0.3 dB with respect to the rate 1/2 AR4JA Protograph. Yeah, so this is it. This was the full presentation. If you have any questions, feel free to reach out.